determine whether the following series converges. Did you notice that for this one single time, I have not called out every single term in the series, and instead I've labeled the series as series? I think that's a good change, because I can imagine how boring it is on the other side to hear me recite every single number in the series. Sometimes I do it deliberately to give myself time to think about the problem. But anyway, as you can see here, I'm pulling out this. You know what this is? It's a tool that we'll be using to solve this type of question. That is the geometric series formula. So there's a theorem that says that if you have a sum that's like this, it's a geometric series, and it's infinite, then this is the value for it, provided the condition that your factor, your multiplying factor, is less than 1. If the multiplying factor is greater than 1, then it won't really diverge, because the sum is getting bigger and bigger and bigger. Like, forget about the sum. Just take the smallest, take the biggest term in this sequence. Take the biggest term in a growing sequence of numbers. There isn't, because it's growing. You see what I mean? To make this precise, so if I take the sequence in which you multiply by 2 with every step, so it's 2, 4, 8, 16, 32, 64, 128, and so on. Tell me what the biggest term is. I don't care about the sum of these numbers. Let me just focus on the biggest term. And the answer is there isn't. For every number you can name, I can always name a number that's greater. And from there, you know that just by looking at the last term in the sequence, you know that it's going to diverge. So you don't even need to look at the whole sum. This is how strong it is if you have a sequence that's increasing. A sequence in the sense of a sum in the sense of this and that, because I want to make my words very precise. And perhaps all of this talk gives you some hint about how this series should turn out in the end. Effectively, what we would like to do, regardless of my comment that I just made right now, is to compare the terms, term by term, and see if we can extract some information out of that. Here I have a 3, and there I have a 1. I don't like it. So what I'm going to do is, I'll take the 3 as a common factor. Then I get 1. Then I get minus 4 over 3. Then 16 over 9 positive. And then minus 64 over 9. Well, it's going to be 64 over 27. And so on and so forth. This is an alternating series. So what's going on here is the following. I think I can compare this to that. So it seems like this 3 was obstructing the line of sight that we had. But now I can compare term by term. And it appears to me that a good candidate for x would be minus 4 over 3. So let me make this precise. By comparison, I was able to figure out that x could be minus 4 over 3. Now to check this, we need to look at x squared, see if it will give us this term, look at x cubed, see if it will give us that term, and so on and so forth. And it seems so. If I square minus 4 over 3, I'll get 16 over 9. And if I multiply this by x once again, I'll get minus 64 over 27, which means that indeed I am able to write this as sequence, not sequence, this series as follows. I could write it as this expression times 3. This x, which I've newly found, is equal to minus 4 over 3. And I'm not sure if you see the problem here just yet, but I hope you do. Because I wish we could apply our theorem, but unfortunately we couldn't, and we cannot. The reason for that is that our multiplying factor is greater than 1 in modulus. So its absolute value is greater than 1. 4 over 3 is greater than 1 after putting it in the absolute value. So it doesn't matter if it's positive or negative, really. If it's negative, it will go to minus infinity. If it's positive, it will go to infinity. That's not the point. But what I'm trying to say here is that this series grows. It grows. And it will continue to grow because with each step you get a bigger term. And in the same sense, you cannot really name the biggest absolute term. Absolute in the sense of value, not in the sense of the sign. You might be a bit picky and you perhaps mentioned to me that this is an infinite sum and you have positive and negative terms, so perhaps they'll cancel out, but they will not. And this perhaps you need to trust me on. Or you could think of the proof of this theorem, which is a very simple proof. And the problem really is with the term that's like this. So the answer is that the series diverges because it blows up. If you want to stay for a little bit more, I'll talk about something that's nice. So in the proof, this is what happens. So the infinite sum is the limit as n goes to infinity of the finite sum. The finite sum is given by 1 minus x to the n over 1 minus x. And this, I believe you have to take as it is. Now, if n goes to infinity and this number is a little bit bigger than 1, then this thing blows up. It absolutely blows up. Minus or plus infinity. Doesn't matter. This thing in modulus is absolutely huge. And because it is, we know that if we don't have this condition on x being less than 1, then you won't be able to make progress on the problem. Because otherwise this 1 will not vanish. It will only vanish if your ratio is decreasing. And that's really the takeaway from this exercise here, is that if your multiplying ratio is greater than 1, then there is no way, absolutely no way, absolutely perhaps as a pun, because we have mentioned absolute values very briefly here, a way that it converges. So that is the takeaway for this exercise. I really advise that you take a look at the proof and think about what would happen if we drop this condition and why we cannot really move forward without it.